Wait, how did you come up with that? You were already talking.
No, because here there is here at U of T, there is a lot of algebraic geometry. And
That's so funny.
most of the junior undergrads, I mean, like first, second years, I mean, with probability one, they will tell you, I want to do algebraic geometry.
The more abstract, the better.
Yeah, this is very funny because, you don't know,
Oh, no.
Urbana-Champaign, they were all doing algebraic geometry. She said she wanted to find something new.
Good.
Geometry, no.
Very good.
Very funny that you say that. That's confirming.
Yes.
No, here really like you take the first like the first year grad students, they only think of algebra.
Too much, yes.
But we hired many good professors in the past few years. Algebra geometry. So
I mean, it's strong.
Yeah,
But that's a tough field.
And the crazy part is that since everybody who wants to do algebraic geometry here, there are like a bunch of professors that are crazy expert and has no student.
Oh,
Nobody know that they exist.
terrible.
This is also quite.
But in other field, you mean, or in algebraic geometry?
Yeah.
well,
The other fields, yeah.
algebraic geometry, there are so many that yeah, okay, you know, it's kind of the pigeonhole principle.
Oh. The algebraic geometry version of the pigeonhole principle.
Exactly.
Your place. That's better.
Okay, let's see. Can people hear me in the online? Yes, okay, very good. All right. Okay, so this one, I was looking over this lecture. This is really dense. This is the most technical lecture right here. But okay, but we'll try. First, I want to make a comment. I want to remind you of the previous lecture. This was I called it the nonlinear cancellation estimate. And it's just an identity that says applying, I should remind you, V equals some perturbed solution. I think it's U, so U still here, X plus psi of X, T, P minus U bar of X. Okay, with this definition, which is a natural modulation, but however, kind of it's reversing the modulation onto the unknown. That gave us, because we did it in reverse, we get, we get only derivatives of psi in there, derivatives of the phase. That's very important because the phase decays more slowly than the perturbation V in everything. That was one point. But I should have emphasized more. There's another point. If we don't put this term here, all these terms go on the other side. And what are they? If we, well, L applied to U bar prime is 0. So any derivatives in the linear operator L pass immediately over onto psi. Well, and also dt. dt minus L kills U bar prime. So it's just U bar prime, which is kind of like a phase shift, times dt minus L of psi. Well, that's linear. This is not decaying, and this is a bunch of, it's not quadratic. These terms would each one individually give a lot of trouble in the nonlinear iteration. They would go if treated as just sources. But instead, we notice, but really it was just like a lucky guess that maybe something like this could be true, because otherwise nothing could be true that we needed to be true. So we check and we see, oh, in fact, they do all fit. And the good thing here is this is sort of like when we, in the shockwave case, it was just, there was only a dt. And it was just dt of psi times U bar X. And that could be integrated in time and we could exactly see what it is. But this also, just pulls the value at time t, right? It's like it integrates it for you, but it's integrating the whole, not just dt, it's integrating the whole linear PDE and getting rid of these terms, which is, I should have said more. I think that's a real key. It took us a long time to find, and that's kind of what makes everything work. Okay, next point. Okay. So there are a few things that are out of order, because actually there's a heuristic motivation that comes before this and really guided us. And this is the Witham modulation equation. If you remember when I talked about Schneider's work, I mentioned he had a amplitude equation and a Ginzburg-Landau, a formal Ginzburg-Landau equation that motivated him. So this is kind of like another version of that. It's just not only for small amplitudes. This is for any amplitude of waves. So the idea is, that you look for u of xt as approximated by a multi-scale expansion. So u bar of k of xt, okay, so k is going to be the period of the solution. Remember that for every period nearby our wave period, there will be a unique solution up to translation. So this is parameterizing the family of nearby traveling waves. And then applied at some phase, capital psi. I'm writing a capital psi to distinguish it from our small psi, which is more like a perturbation in capital psi. When we do shifts, it's a shift of a background wave. This is not a shift of the background wave. It includes the background in this heuristic. Okay, and what it turns out is, and I'll show you on the next page how it turns out, but it turns out that this is consistent up to a fairly high order in some sense, and it suggests that the period and the, okay, so this is the omega is the time frequency for a given wave frequency, right? And so this is actually omega of k here. So this is a scalar conservation law. It's like a Burger's equation. So that tells really in the large scale how this pattern is evolving. It's just a periodic pattern, and its period, or you could think of its, well, both its phase and its shape, which depends on the period, are evolving locally. They're varying in this very nice way. Okay, since it's scalar, this is always hyperbolic. Every first order scalar is hyperbolic, and it has a nice evolution, and it's predictive. Okay, so this is out of order in two ways. It's out of order because we proved a theorem that in our minds was motivated by this. We already proved it, but we didn't mention this yet. But also, it's out of order because Witham developed this system of formal asymptotics for the KV equation for systems, much more complicated. And it was later applied by Nancy Coppell and Howard, I forget Howard's first name, to multidimensional reaction diffusion equations, which somehow, and it's, when you see it, it seems that should have been the starting point. It's much simpler to derive it, much more clear. It's completely out of order, but also that made it hard to find, I think. Hard for them to make a jump and say, oh, maybe it's something like a Witham equation also for reaction diffusion. And I think that was a surprise for people. So that's a really nice result. And here is the really nice argument. Yes, for sure. But again, I don't think he did it for reaction diffusion, right? But it was always a system. It was always rather complicated with Riemann invariance and things. Well, that's my understanding. But yeah, so yeah, for sure this is Witham's idea. So here's the derivation. So let's see. I think I skipped one comment. What did I do? Yes, very important. We're gonna rescale xt to epsilon x, epsilon t. So basically, we're taking the large scale, 1 over epsilon scale, down to order 1. So whatever we get in the finite time limit should be the large time in space behavior. Whoops. Let's see. Well, this is in the ordinary scale. It's funny. You do it in the epsilon scale and then you pull it back and get this. But the derivation is done in the epsilon scale. You'll see why in a minute. Otherwise, you don't know what to do. There's no small order. The idea is we're going to, well, let's see, it's better to look at the equation. When I rescale it, it looks like this. So you can see it's singular and it has high frequency period epsilon waves, really, and epsilon is small here. And then we take this approximate solution. Now the multi-scales are present. They weren't apparent before. So we want two scales. We want a fast scale for the phase because we expect rapidly oscillating waves. And then we want like a bigger envelope depending on the slow variables x and t, and then higher order terms as usual. Okay, so if we so expand it by chain rule, plug into the equation, expand, and match terms. At the epsilon inverse order, you get this equation. And well, okay, so here, theta is the fast variable. I don't want to always talk about psi over epsilon. I'll just call this the theta variable, and psi over epsilon happens to be there. Okay, so when you write it like this, then all the epsilons come out and you can compare them. Okay, so what should this be? Well, this is the, if we set k equals psi x, omega equals negative psi t, and plug those in, we get the traveling wave profile ODE. So this is telling us the biggest order tells us it has to approximately solve the profile ODE, which is not, I mean, the whole idea is kind of really surprising to me how great it is that you perturb a periodic wave, rapidly oscillating wave, and it just kind of moves in the nearby family of waves, just little pieces of them, and they glue together through k and omega in this very nice way. That's a remarkable picture, very informative. Okay, so, all right, but we just solved it because from k equals psi x and omega equals negative psi t, equating mixed partials, we get the Witham equation. Here it is. So that's all there is. It's much simpler than what Witham had to do for KDV. There's a lot to do. You have to work out a lot more things. Here it's right at the surface. But okay, if you continue, oh, and maybe I'll just mention, what is the phase velocity is omega over k. This is the spatial frequency. This is the temporal frequency. That's just the speed of a single traveling wave with a fixed period. But now we see the behavior, the envelope, roughly, it's behaving according to this conservation law. And here it propagates with characteristic speed alpha equals omega prime of k. That's called the group velocity, or it's a nonlinear group velocity, I would say. And it's different. So you see a lot of interesting things here. And you can understand things about patterns also in multi-D from this picture. Okay, but if you continue to higher orders, you can get a second order. Here it is. A second order Witham modulation approximation, and it turns out to have a diffusion. Okay, some diffusion. So, which I won't describe, but big K. That was at. I think it's a typo, but it also could. Usually, I would use K star. It could just as well be. No, it's a typo. This is a typo. Here, yeah. Right. And this is very similar to what was motivating Schneider, but he considered the phase itself, right, which is the antiderivative of this. This is a conservation law. The antiderivative would be a Hamilton-Jacobi equation, which makes sense for a phase of an envelope of waves. Okay, so very similar. Okay, okay, so now, so I showed you the nonlinear iteration, and I got a little worried that there might be typos in the decay rates and so on, but they were all exactly correct, actually. what's confusing about them is they're not the usual numbers. They're too good. They give you extra. This is a rare example. It's a nonlinear iteration that closes with room to spare. Okay, and to understand that, we could notice, well, okay, so what's the kind of data we're looking at? We were looking at localized data, so perturbations that are in L1 or L2. Okay, so that's like psi in L1. But that means K is the derivative of an L1 function. This is a Burgers type equation. What are we linearizing around? Well, the background wave is a periodic wave of constant period. That is, in this setup, that's a constant solution. That's K constant. So it's like the first things we did where we linearized around a constant solution, and by studying the heat equation, we got nonlinear stability. And so if you remember, the derivative of a heat kernel decays faster by t to the minus 1/2. So we have some extra decay when psi is localized. In this lecture, we're going to consider K localized, because think back, for the heat equation, that's all we needed. We didn't need that it be the derivative of an L1 function. We need just that it be L1. And we expect decay, nonlinear decay at the rate of a heat kernel to come back. We've done that many times. And that's what we'll get. And there all the numbers will be familiar because they're exactly the same as the shockwave lectures. Okay. Okay, so that's what we're going to prove. But I'll just mention something that's, this is the hard part of the whole analysis. So I said that, so here's a derivative. So that kind of, a derivative of a source, that's helpful because it means the derivative hits the propagator and makes the propagator decay faster, and that's what makes the argument close. Think of this as basically, well, there's a linear part, and then there's some quadratic leftover, which has a derivative. If it were just the quadratic leftover, it wouldn't converge without the derivative. So we need that. But now, in our solution operator that we wrote down, it was rather complicated. It passed through block inverse transformation, and it doesn't look like I mean, there's always a U bar prime, which is just a derivative of the background periodic. It's just a non-decaying periodic wave, and then some other things. If an X derivative hits the U bar prime, that's bad. It's wasted. It's not making anything decay faster. It's just making a non-decaying periodic function into a different non-decaying periodic function. Okay, so that's what we're after here. In the previous lecture, we still had that problem, but it was a bit hidden because we didn't look carefully at the estimates. But by separating the phase, we were able to find that somehow derivatives sort of the difficulty I just mentioned is with the phase shift. By removing the phase shift and treating it separately, we got around that, and we saw that our intuition still held, and derivatives of the wave are still good. So we're going to do that here in a stronger way. Okay, so I'll just remind you of the preliminaries. So L was the linearized operator around the wave. LC was the block transform of that operator. We assumed it had negative real part spectra, so stable, and departing as C departs from 0. This is moving quadratically to the left, and lambda equals 0 is a simple eigenvalue.
So 0 is the non-decaying back.
Yeah, 0 is translation invariance. And so therefore, taking these together, we have that there is an analytic eigenvalue and right and left eigenfunction, the critical mode or the neutral mode bifurcating from 0. So we give them a star. Lambda star is negative IXC. That's the eigenvalue plus, big O of C. But in fact, we know more. It has a negative C squared times something. And then eigenvector right and left. So the right eigenfunction is Q star at C equals 0. That is the derivative of the traveling wave. So we know Q star is 0. Q tilde we don't know, but it turns out we're not going to care too much. And there's an associated projector, which is just the pairing of Q star and Q tilde. It's rank 1. This we did before, and then we broke the solution operator, which can be written as an inverse block transform of the solution operator for LC. SC is the solution operator for the transformed guy, and applied to the block transform of the data. And okay, here's what LC looks like again. I'm just reviewing things that we did. And we split the full solution operator into a principal part or phase part, and then the rest. And the phase part was U bar spatial derivative times SP of, this should not be, okay, this is of T, but it's something that, it's a function in X and T. This is a solution operator acting on the data and going to another function of XT, and then the rest. Yes.
Localized data or localized data?
No, this is going to be non-localized data, but so far, all I'm saying here is applies to both, of course, but we're going to do non-localized data. You'll see. And here is the key point is that this SP, here's how it looks. It expands. Here's the rank 1 projector that we just defined on the critical mode. Here's the solution operator on the critical mode. It's just e to the lambda star of CT. And then e to the ICX is the transform. All right, so let's just look at this a minute. This is actually, there's spatial dependence here, but we take an inner product, so that's integrated out. There is no spatial dependence here other than in e to the IXC. So this is interesting. It's actually an inverse Fourier transform, which is nice because more familiar and easier to work with. There's no block here. That's because we removed the U bar sub X. And here, alpha, I remind you, alpha of C was just a smooth cutoff function to keep everything near the origin, near C equals 0. Otherwise, we have to stay within the domain of analyticity where this works. Okay, that's what we had. And this is still review. We proved these basic linear estimates, which were like that SP takes L1 data to LP at the rate of a heat kernel. Oh, sorry, LQ data to LP at the rate of a heat kernel. Derivatives work like derivatives of a heat kernel, except we don't keep track after the first one. There's a -1/2. Here I've assumed that there's at least one derivative by writing this gradient here. And after that, we just say the other ones are better, no worse. And then the rest, it also decays faster, like derivative of a heat kernel. Okay, those were our basic bounds, and it's surprising we don't need too much more. This was sufficient for localized data. We need one more. Okay, and here's the main new ingredient. We need to be able to treat, we call it a linear modulation estimate. And let's see, just look at the first line here. I'm having trouble seeing this. Okay, so this says that if we apply this phase operator to special data of the form H0 times U bar prime. So what is that? That is like that's like modulated data, but the linear version. Because if you take, that's like U0 of X plus H0, or sorry, U bar minus U bar of X. That would be approximately U bar prime, H0. So this is just capturing or approximating what modulation initial data would do. And so we're going to allow not only perturbation of U bar we're going to allow a localized perturbation in any direction of any sort, but also a phase shift by a function H0 that is not localized. Only that its derivative should be in L1. In particular, it could have different values at plus and minus infinity. In general, it would. So that makes the behavior more interesting, and it makes the decay slower, much slower. Okay, so here is the key estimate. Remember I said the whole trick to this, the intuition is that x derivatives pass through onto k. So somehow derivatives have to pass through all this SP nonsense that we have onto H naught U bar prime, onto the data. And that's what this estimate says. It says I can put the derivative onto H naught when I have special data of this form. So it has to be modulational. It has to be multiplied by U bar prime for this to work.
What bubbles that goes to H0 to originally you had any derivative?
Oh, yeah, I have many derivatives. And once again, I don't care. I only want to make sure one of them will pass through. And after that, it's not important for the argument. But I will have to treat more than one derivative. So I have to, I need to estimate them, but not carefully. That's what I mean. Only the first one is helpful, and the others they don't hurt. That's the idea. Okay. And yeah, and so here, yeah, so I assumed this is space plus time derivatives have to be at least one together. This is the key assumption. Otherwise, I have nothing to pass through.
One?
Yeah. Uh-huh. Yes. It's nice. Yeah. And then, okay, and then the rest says, okay, but there was S tilde that's like the rest of the solution operator. That one also works. And this time, you don't need to have even one derivative. This just says, yeah, there's zero, or there could be some, and this big K actually puzzled me. That's the level of we carry out the nonlinear iteration later, up to like to HK, capital K. So that's all it is. I'm just saying it's arbitrary. Pick any capital K and we can prove these estimates. As long as remember there was a function in the original reaction diffusion equation, the source, G of U, that has to be smooth enough so that our linear solution operator is smooth enough. But that's the only restriction here. Okay, and for t less than or equal to 1, well, this is yeah, for the localized data case, there's some initial layer problem between our linearized picture and the actual nonlinear picture. Well, as you can see, this isn't exact, right? What I did here is not exact. So there's going to be some issue there. We took care of it easily in the localized data case by just setting SP to be 0 at t equals 0. We're not doing that here. So we're going to do something that's like that, but a little more careful. And to do that, we just have to know that SP doesn't change things too much. In the sense that, again, we can pass the derivative onto H naught. And that's all we need. And then bound it by, well, just 1. That, like a Gronwall inequality, but that the derivatives do pass in. And here, yeah, okay, so this is the same. The two are the same. Okay. Yeah, this is only for t small, because we're going to have to do something for t small. We have to make some adjustment. There's an initial layer between where this Witham description is correct, and then at time 0, it's not quite correct, or at least not the way we've expressed the Witham stuff in terms of a certain nonlinear iteration involving all these linearized bounds. Yeah, these are for t large. They're for all t, but we also need a tiny bit of information here, just to say that things don't change too much when measured by the L1 norm of H naught. See, we want H naught out of the picture. H naught is not localized. It doesn't give any good bound, but if our solution operator applied to dx, H naught is good in subset. And here's, yeah, the moral is the x and t derivatives sort of pass through things. And this it wasn't clear at all from the beginning. But by this time, we had really learned to trust the Witham equation. We really believe in what the Witham equation tells us, because it worked time after time, this formal thing. So if the Witham equation is correct, this has to be true. So we worked very hard to see how it could be true. And so here's the proof. Okay. So I'm just gonna, I think I'm just gonna focus on case one, which is the primary mode, the phase mode, little sp. Okay, so I'm gonna go line by line here. So dx of little sp. Okay, so remember, this is a Fourier transform. So dx is just IC. So that's where this IC came in. And everything else is just written from the formula for SP. So there's the alpha, which is just a cutoff. There's the time solution operator. There's e to the ICX for the inverse transform. And here's the projector. And let's see. And what if, let's see. Oh, sorry, it's here. Here we go. This is what I want. Okay, and really the U bar prime goes over here with the H naught, but I just moved it over here already in preparation. Okay, this is, let's see, right. And this is H naught hat. And we have to, or not hat, check, which is that is the block transform of H naught. And so we have to remember what the formula was for that. It's gotten from the Fourier transform of H naught by expanding, by summing over all integers j, the Fourier transform of H naught applied to xi plus 2j pi and multiplied by e to the I 2 pi jy. Okay, so that is the only spatial, the only spatial dependence in H check is here. And I've pulled out the xi dependence out here. So in the inner product, it's only we only integrate against y. Okay, so I have this. Well, now I'm going to have to sum it in the end.
0, it's for which variable? So
That's in y, yeah. Yeah, I tried to help by writing it in y here. By tilde of y, yeah. So here I didn't put the, right, I didn't put in, this is a dummy variable y. Okay, and now here is the, okay, here's one tricky part. I noticed that this is just, now I moved the u, let's see, I moved the u bar prime back over on the other side. So that makes me wonder why I ever put it over here, but, and I noticed that's e, oh, no, that's right. This is why I did it. This is the inner product of e to the I 2 pi jy against phi tilde u bar prime. That's the Fourier transform, the Fourier series for phi tilde times u bar prime. But with, it's the complex conjugate, actually. So the star here is complex conjugate, because I was having trouble with symbols of this product. Okay, so now we're almost done. The last thing we do is we notice that, okay, this is the tricky part. We want to write H naught hat, which is the Fourier transform, as the Fourier transform of the derivative divided by its argument. And that is true. That's absolutely true for everything except for the zero mode. For j equals 0, it's a little tricky because that the zero, let's see. Let me put it a different way. Here's H naught. If H naught were just a Heaviside function, which it kind of is, that wouldn't be true. You need it to be balanced. You need to first do, this is an interesting, fun technical fact. You have to first shift things so that H naught at plus infinity equals negative H naught of minus infinity. And then it's true that H naught at equal over IC. Okay. Then my formula is true. How do you see this? Yeah, it's actually, not so easy to see, but basically IC is odd. So you have to respect symmetry. The only way you could, if you take Fourier transform of odd, it's got to be odd. So it has to be this. And you know it, some shift has to work. This is therefore the shift. That's my quick proof. Yeah. Okay, so you have to, other than that, small technical thing, this is clear. And now that's good because this C that came from the derivative is exactly balancing this term. This term is bad for J equals 0. There's only one mode that gives us trouble, but that would give us a lot of trouble. That would kill the argument, but here it cancels. And so now we can estimate everything putting together. Oh, okay, wait a minute. We can, but how do we do it? We do it by Hausdorff-Young, term by term, and then summing. Remember, this is now just a Fourier transform. So when we take Hausdorff-Young, we're bounding the LP norm of this of this full function by the LQ norm of its transform, which is everything except the e to the ICX in here. Okay, so the LQ norm, this one we're going to pull outside as a L, just the soup of this. This one we're going to pull outside as a supremum. And this one also as a supremum. That leaves us with the usual thing, e to the lambda CT. The Q norm from all our other lectures is known to be the decay rate for a heat kernel. So that puts us here. So this derivative of U bar of SP on U bar prime H naught is bounded by the decay rate of a heat kernel starting from L1 data times, okay, the L1 norm of dx H naught bounds the L infinity norm of the Fourier transform. That's what we pulled out. And then we also pulled out some other suprema, which were these.
H0, what are the variables for H0? Just X and
H0 of X, it's just X.
sometimes H and X and C because of block.
Well, no, because this one is just the initial. This is only in X because it's the initial datum, H naught. Okay. Let's see.
So the people add opposite add.
Let's see. What are we doing here? This is the no, because H naught is on the whole line. It's a Fourier transform, not a series. So here it's H naught check. And that, so what did let's see. Yes, that started as block, yeah. But then I wrote down the block as in terms of the Fourier transform. I converted that over because yes, yeah, it's it's a bit involved, but yeah, I had to go back and look at this line by line. I confess to prepare this talk. It's you have to make all the right steps. But now this takes us to the L1 norm of the derivative. That's what we wanted. The decay rate we wanted, and all we have is multiplied by some series. But this series is nice because it's perfect for Cauchy-Schwarz. It's if we take the L2 norm of 1 over 1 plus j, that's just a constant. So then we get the L2 norm of the rest. And that's our bound that was up there. So it's a little bit, yeah, no, it's okay. This is the key part. This is the main thing. Phi tilde, that was the left eigenfunction. The neutral mode. Yeah, we have to, yeah. That came, yeah, it's up at the beginning. Yeah, it survived, it passed down. That one survived. A lot of things didn't survive till the bottom, but that one does. And there it is, yeah. But okay, so now we finally have an estimate. And that's because, so this is harmless. This is on L2 of 0, 1. Both of these are nice bounded functions in lots of derivatives, so that's just constant. Yeah, so that leaves us with a big constant from this sum times what's above, and what's above is our bound that we stated. Of course, there were stated two other bounds. You have to do them. The other bound 2 was on the rest, on S tilde, the remainder part. And there, I'll just remind you, we had to, the remainder, of course, involves several different terms. One because of the cutoff, correcting for the cutoff. One for all the other modes, the complementary modes. And then another one was we approximated phi everywhere by u bar prime, which was its value at xi equals 0, but not elsewhere. Okay, so we have to correct that. But each of these correctors has a power xi. Like this is just Taylor expansion gives us a xi. This one because pi tilde on u bar prime is 0. And so to order xi, it vanishes. And this one, let's see, why is that one not? Again, alpha at 0 is 1. So this is just Taylor expansion, order xi. So there's an order xi. That's like the derivative that we started with, and we have to trace the estimates through similarly as before. But it's not so bad because the only hard one, remember, these two were exponentially decaying, if you recall. So just having the xi, that's enough. That will balance things and allow us to pull out to follow all the same steps. That gives us a way to get the derivative onto the u bar prime, and then we have to worry about the time evolution bounds, but we don't have to worry. They're time exponential. So these two are easy. This one actually is the same as what we did before. So it's not so bad. It just looks bad. It's actually once you've done the other one, this is the easy one, even though looks like the same. The slide looks the same, but it's much simpler because there's only one difficult term. It's the same as before. So I'll pass on this. Okay, and then on step 3, I'll really take a pass because that was just trying to say things stay close to their initial values. But there I can use a time derivative bound, which moves the derivative onto u bar prime, and use mean value theorem. This one's really easy. Okay, so, all right, so I assume I've escaped out of these slides. We got through the marsh. But that's really that's the new thing. Somehow you have to understand that, a new way that derivatives pass through and act like with a modulation. Okay, but there is one little tricky thing. Okay, so now we'll modify our iteration scheme slightly. Okay, so we start with the same V as before. We use the same cancellation estimate as before, but at time 0, at time 0, psi can be initiated as H naught. It will be initiated as H naught. Some H naught. Balanced, where we choose it without loss of generality so that its value is at plus infinity is the negative of the value at minus infinity so that our estimates work. Okay, now we're going to choose psi to cancel the contributions from SP in the solution operator. Okay, maybe this should have had a quote because we can't completely cancel it. The top, okay, here is what we want. This would completely cancel all the SP contributions if we, let's see, if we just set, where is it? Here it is. Sorry, here it is. If we just set here it is. Yeah. Okay. This just as in the previous case, this would cancel everything. The bottom term, though, shows we're actually interpolating between that, the perfect cancellation, and this, which is perfect matching of the data. The top one perfectly cancels everything, but it doesn't match the initial data, sadly. It matches it to linear order, but not nonlinear order. and that's no good. So instead we take 1 times this plus 1 minus chi, where chi is like smooth cutoff in time. It's 0 at for small time. Okay, so at small time, what do we get? This is really, I've sort of hidden it. It sort of has a chi in front of this because I put a minus h naught in there. Let's see, no, where did it go? No, I put everything here minus h naught. Okay, that's another way of writing interpolation. I'm going between total cancellation and h naught, which is perfect data. Okay, but this will be fine. It will give us then, plugging that into our V equation, we get what we had before, this nice term, but now we have also a leftover term with this cutoff. Okay, so this cutoff for small time is 1. This is playing a role, but for large time it's gone. And our small time estimates for SP and are fine to control this. Those were pretty trivial. So it took us a while to find this way of doing it. I think it's a decent trick. There's another way, but that took care of that problem. In a smarter way, what we did before, well, that was smart for the localized data case because it was very simple, but it wouldn't work here. Okay, so once you have that though, now, so you should ignore here these terms because you just split it into time 0 to 1, and there's really only this term, and it's simple, or time 1 and larger, and there's only this term. And now it's not simple, but it's the same as our analysis of stability of a constant state for a Burger's equation. And okay, so now we do all the usual things that we've been doing. We differentiate the psi equation in x t. And we remember that n, the nonlinear source term, that is, whoops, remind you that what this is the solution operator applied to the data. That's the homogeneous part, plus the inhomogeneous part is the Duhamel formula for the solution operator applied to the nonlinear source term. The nonlinear source term came from the cancellation estimate. It was something that depended on V and derivatives of psi, not on psi itself. Therefore, we can differentiate this equation, because this is not a good equation. This doesn't decay fast enough for us. We want psi to decay a bit faster. And so we differentiate this in x or in t. And now we're back to the differentiated bounds on SP. Our modulational bounds, so right here, first term in the whole right-hand side is a modulational type bound. And we will have a derivative in front of it, however, so it will decay like a heat kernel applied to the derivative of h naught. And the derivative of h naught is in L1.
H0 from, because
Oh, the minus h0. Okay. Yeah. Yeah, the chi is not written, but really, so there's a 1 minus chi times a copy of this. The copy is everything but the h naught. So if I put that up here, I would then have a chi. I would have 1 minus 1 minus, there would be a chi in front of this and only an h naught here. I could put a chi in front of the first term and keep only an h naught in the second term, but I actually prefer to do it this way for the later estimates. But it is just linear interpolation between this first term and h naught, just written in a non-standard way. Yeah. Yeah. And okay, and now we've solved this exact system before. It's the same system. So we're going to get decay at the rate, expect decay at the rate of a heat kernel for both V and the derivatives of psi. So here's the theorem. So let's see. It says that if we have a small enough norm E naught of the shifted data plus the derivative of H naught in L1. Then there's a global solution U tilde with this data U tilde naught and a phase function psi with data H naught such that for all high norms, p between 2 and infinity and times positive, we have the bounds that we expect. We have that the modulation error decays like a heat kernel. The derivative of the phase decays like a heat kernel with amplitude E naught of the initial data. And if we take the HK norm, it's the same as the L2 norm, and it's just 1 plus t to the minus a quarter. Furthermore, if we take the unmodulated error or the undifferentiated phase, those are bounded in L infinity by E naught. So this does not tell us convergence to a phase, to a limiting phase, but it does tell us the phase remains bounded. So it's like it's an asymptotic orbital stability result, a bounded nonlinear stability result, but not phase asymptotic. And the orbital stability, well, what is the orbit? It's all modulations of this periodic wave, which is not the same as a usual orbit. Those would all be other steady solutions. These are not exact solutions. It's like an approximate center manifold or something, but it's not really a center manifold.
H0.
We're saying, no, that's a perturbation. That's an allowable kind of, yeah, so there's two allowable kinds of perturbation. One is the difference between a shifted background periodic wave shifted by H naught. Here we put the H naught on the other term. And, okay, that's one. So that's V. And here's the other thing. The derivative of the shifting of the phase must be small n L1. But that's not a localization bound. That would be L1 norm of H naught. So the phase is not localized. It can go between two limits. And all right, let's see. So I'm going to, I mean, the important part for us was improving the estimate. That was a difficult estimate, but I think it's not important to go through the nonlinear stability argument because it is the same. Now, it really is the same. We're just going to do the same bootstrap argument that we've done over and over, but we'll do it just in L2 and H3 to start with because it's handier. And there is one interesting thing to mention. And for this, I have to go back. Whoops, back. Here it is. Remember, there's this very strange k plus 1 that I couldn't remember. What this is indicating is if we're going to do our nonlinear iteration in k, it turns out that when we write out the perturbation equations and do the nonlinear damping and so on, it turns out there are some extra derivatives of the psi. That looks bad at first glance. But then you notice this SP, it's really more like a Fourier transform, and it's all in low modes. It doesn't have any singularity. As it's all 1 plus t to the minus whatever. It doesn't blow up as time goes to 0. It just has extra factors of xi in there, and they don't hurt. So they can only help. What it means is this SP is infinitely smoothing. So the phases that you get, we've chosen them in a way that's very convenient for analysis. We can take any number of derivatives in there, and it's fine in the argument. So it's only that V, the bulk perturbation, has to be controlled. Let's see. Yeah. So I'm controlling V, but also derivatives of psi. So those have an extra derivative. And okay, so when we bound the nonlinear source term, we get something. Okay, it's fine. We get something that by definition is xi squared, or sorry, zeta squared times 1 plus t to the minus 1/2. That's what we had always in the past. That's the L2 norm of it. And then, sorry, the L1 intersect H1 norm. And then plugging that in everywhere and using our linearized estimates, here are the bounds we get. So the LP norm of V would be the decay rate of a heat kernel applied to the L1 data. This is the homogeneous part, plus C zeta squared times the derivative of, so it's a differentiated heat kernel because we managed to pass derivatives onto the source. And then the source is always 1 plus s to the minus 1/2. That's the previous slide. And this nicely, when you integrate this, you basically add 1. So that kills this one minus 1/2 and this minus 1/2. You're left with the decay rate of a heat kernel. But now times a big constant, depending on P though, times E naught plus zeta of T squared. That's the bootstrap estimate we were trying to prove, exactly this. For psi T and psi X, exactly the same. And that, okay, and that gives, but that also, the psi bound can be in as high an HS norm as we like because it's smoothing. Now that gives enough to carry out a nonlinear damping estimate for V, controlling the H3 norm of V by the L2 norm of V plus the H4 or 5 or wherever we are norm of psi, sorry, H4 norm of psi X. And that gives finally the desired HK decay rate for V. Okay, and okay, if we cycle these, now that we have something, we can cycle it back through our estimates and we get the LP bounds that we claimed. For any finite P star, because I wrote a CP, a big constant depending on P, on the norm P, it actually blows up as P goes to infinity. So you have to treat that case by a different bootstrap argument. Basically, you have to put, the problem is that we put the L1 norm on the source and we tried to put all the decay on the propagator. You can't do that. You could put the L2 norm on the source and less decay on the propagator, then it works. That's the answer. Right. So, but that's a detail. And we just noticed we got slower decay by a factor 1 plus t to the 1/2 than in the localized data case. It agrees with the prediction of the Witham equation. And it's not for the localized data, it was actually an asymptotic stability result. It converged to the original periodic wave with no shifts. And here it converges to a modulation of the periodic wave. Okay, so that's where we are. Okay, so we stop. Wow. Well, I cut out a few things to make it fit, but my planning was good. Okay, so now we usually take a break, so we'll have a break and then we'll try the Witham equation. Okay, I apologize for coming in on the end of a story. There's some references to earlier stuff, but it's too involved to repeat. Sorry about that. I hope you get the general picture.
It's nice that all these guys kept, you know,
I really-
listening to,
I'm impressed. Yeah.
I mean, I don't know if those who are not visible are present, but
Oh, yeah.
yes.
Yeah. Yeah.
Don't they?
Yeah, those are my two students. So maybe they felt obliged. I don't know. Yeah. Yeah. Mhm.
That's nice, because if you wanna change it, 2 years is not enough to like. Do some bigger count selection.
That's true.
Okay, we got everybody, right? Yeah. Okay, so let's continue.
I have a small logistic question.
Yeah.
Next Thursday, we have 2 hours or just 1 hour?
I have 2 hours
Okay.
listed.
Good, because
You have
I was
some-
checking I was checking my calendar. I said 1 hour and I wasn't sure.
Wait.
So,
So
Thursday, we have Federico seminar 1:30 to 2:30
and then 2 hours I tried to change to that because we canceled 1 hour for the Vigdison talk and I put it at the end, I thought, but maybe it doesn't say that in the schedule, does it?
it's my schedule, so I just wanted to make
Oh,
sure. it
oh,
wasn't-
oh, okay. I think on the web page, I think it's changed to
Okay,
two.
I should have checked the web.
Sorry, there was a lot of changes right at the end, but
we should break the end of the course with a beer somewhere.
excellent.
Aperitivo we do.
Okay, all right.
In Italy, we have this stuff, aperitivo around 5, 6, 7 p.m.
Mm-hmm.
Beer, something to, yes.
I like it. Yeah, very good. Yeah. I was afraid you were going to quote the cite the French system because then the guy giving the talk has to make the poll as well. We could just get a beer. That would be great. Okay, assuming we survive the next lecture. Okay, so this one, oops, we're now going to justify this with a modulation equation so that we can extract the behavior and that it does coincide with them. Okay, so I'll write it again. This is the approximation we have in mind, and then okay, and it's indexed by the wave number k, and that's changing slowly, and then the psi, which is changing rapidly. Okay, so the first, I'm sorry, psi is no more changing rapidly. It's only in the epsilon variables. Here it's just changing order of one. Yeah, as the background wave. Okay, but we got this from this Witham thought experiment. Okay, and what? The first stability result was based on this identity, that the derivative of the traveling wave was equal to the right eigenfunction. That's it. Okay, but we need to do more. That allowed us to separate the phase from the linearized description, finding some cancellation, and phase modulation. Okay, if we go further from the traveling wave equation, taking the variational equation for the left and right-hand sides of the traveling wave ODE, we get, the left-hand sides of this basically, we get this identity, that the variation in K is the derivative in C of Q. It's a very nice formula. Times K star. K star is the background, the period of the background wave. That's where we're differentiating. Okay. So that's taking variations of the left and right hand side of the traveling wave ODE. No, it's not so complicated. No, you write down. Well, remember that Q satisfies the eigenvalue equation. And at C equals 0, the eigenvalue equation is the linearized traveling wave equation. And so that gives you an idea that there could be a relation. And this is the relation you get. I would almost try to reproduce it here, but I'm sure I would you know, if I were in practice for this, this is not, it's not so hard, but you have to be in the mood of getting these identities. It doesn't work well to come back years later. Yeah. Okay, but so this is the idea. Now, if we make use of this one, in addition to this one, now we're going to be able to separate out the modulations in K, because you know that's what this is, the modulation in K. This is the modulation in psi, the derivative. Let's see, I think there was one more thing I wanted to say. No, that's it. Okay. So there's a comment that, okay, in Schneider's original analysis, maybe you remember, in that one, he didn't need to separate the phase, actually. I mean, he did in a way, in that he had to find a lot of cancellation. And he was able to then pull out the behavior by just looking at a next order term. He didn't have to do a nonlinear iteration over again. He just looked more carefully at the solution and pulled out the main part and said, this is the behavior. And we can do that here too. So this is the first result. Okay, so we're going to get a faster decay to something that is the behavior. And then later and after, we'll show that that thing that we get has the behavior of the Witham, that it connects to the Witham equation. Okay, so S is going to be now called RP instead of SP plus R tilde. And RP is going to be the old U bar prime times SP plus something new. The SP doesn't change. That's interesting. And that is kind of similar to if you follow the derivation of the modulation equation, it kind of goes this way. But this will be enough now. Why? It's going to make, remember that SP was this. It was the projection onto phi of C0, but then multiplied by U bar prime. And let's see. Yeah, okay, no, this is the important thing. Now, R tilde, okay, what's left, and R tilde will be, okay, the 1 minus alpha part, the alpha, the pi tilde part, the complementary projectors, and then this part. Okay. This was an error term. This was our only bad error term. There was an exponentially decaying error, exponentially decaying, and these didn't change. Only SP has changed now. Okay, we previously had just phi of x cx minus phi of 0x. We've taken out the next order Taylor expansion term. Now we have an order of c squared. We have something faster decaying by t to the minus 1/2. And that's going to give us automatic faster decay, because the other terms were already decayed as fast as you could want. This was the only bad one. And then meanwhile, something will happen with RP, it's a more complicated description of what's happening. It's not just U bar prime, but two things. Okay, and then we'll get this. Okay, now, similarly, we'll define a modulated nonlinear perturbation variable, modified, which subtracts out the phase, but also subtracts out what we expect to the Taylor expansion of a modulation in K. Here we had to be really careful and not do we didn't do a Taylor expansion. We did it in a nonlinear way. That was because we were at a critical exponent where we could not afford to lose any decay anywhere. This is not critical. This is decaying faster than the rest. We can estimate this very crudely. This is just Taylor expansion. K bar is the background, is the period of the background wave. Sometimes I write K star, so sorry about that. K bar is the background wave, U bar is the background period, U bar is the background wave. Okay, and so that is what? That is the previous V, what we had before, with a new term. So this is the phase modulation, and this is the amplitude modulation, or sorry, I'm sorry, the amplitude modulation through, well, let's say the wave number, the K modulation. So it's pretty crude. But now, if we write we use the same psi as before. Nothing changed. There's not a new iteration. It's just an estimate now. And we write down the Duhamel formula. We get Z is R tilde applied to the initial data plus a Duhamel term in R tilde. And then remember, there's this funny interpolation with the initial data, just the same. And then, okay. And then we've got an RP.
The two Z, I mean, the one on the top equation and the one on are the same, even though there is no X.
Yes, yeah. Sorry, I'm suppressing the S here by to fit Beamer, basically. Yes.
Just make sure I'm in the right place.
Yeah, for sure. And then, right. Okay.
Bar, decay U bar, does it have something to do with in your first slide you had this red line that was
Yeah, it's decay. That's the variation in K of U bar at K bar at the background frequency. So it's a Taylor expansion.
earlier you had this expression, what was it?
It was the
Reduced.
Yeah, it was and that played a role. That played a role in the linear estimates, right? Because it's the variations in Q tilde that mattered for the estimates, but now for the nonlinear iteration, it's this one that matters. This is the only one that matters for us here. Now we're in the spatio-temporal setting before we were in the frequency setting. And the link is the identity the red identity. Very nice. Oh, and I even wrote it on the board, but I forgot to mention this, but this reminds me very much of all the discussions. This is joint work with Matt Johnson, Miguel Rodriguez, Pascal Noble, and me around the ones I show you here. I just showed, and this one are in 2012, and there's another one for systems that I'll do in the next lecture in 2014. And you know that one well, Catherine. That was we got a prize for that one. Yeah. Right. Okay. No, these were before, and then we saw how to do it for systems as well. I'll describe that. Things more like KDV, actually, more like the original Witham. Okay, so now the refined stability estimate, well, doesn't look quite as good. Remember, so this is the LP norm. What should LP be? Of V of the old version. LP was at the rate of a heat kernel, so it went between T to the minus 1/4 for L2 up to T to the minus 1/2. Here we get, well, up to a log term, T to the minus 3/4. It beats all of them, but not by so much. And that's because, sometimes you get some extra decay and you can't use it in the estimate. It just makes something integrable and that's it. And the rest is wasted. That's kind of what happens. But here is the bound. Okay, we have, using our improved bounds, Z, LP, will be bounded by heat kernel with minus 1/2 decay times the initial data. So far, so good. This is what we would hope to get for the whole thing, but we don't. And then, let's see, here is the same decay rate. It's a derivative of a heat kernel with 1 T to the minus 1/2 extra decay. And then 1 plus S to the minus 3/4. That is just plugging in the source. Yeah, the H1 norm is this. Okay, so if we do this is what we get. Carry out that integral. Basically, this is the limiting factor. It will be on the integrating from T over 2 to T. This is just integrable. It doesn't give you extra decay. This one gives you all the decay that you get, and it's T to the minus 3/4. And in fact, the other one's even kind of worse because, let's see, for P equals 2, that gives a log term. You can see it. you're just t to the minus 1. And that explains all the parts. So it's kind of, doesn't fit any particular intuition. It's just what you get from the improved estimates. It's not an iteration anymore. It's not implicit. It's just estimating, writing it in Duhamel form and estimating. Okay, so this was really easy, this upgrade, compared to all the other stuff. That just a computation. And we see, okay, it's faster. Ignoring the log term is, t to the minus 1/4 to t to the minus 1/2 faster. So it is. So that means that the part we pulled out is the behavior. Of course, to really prove that, you need a lower bound as well, right? You need to show that the first bound for V was sharp. But if the bound for V was sharp, then V is the behavior. Then this part that we pulled out is the behavior. Okay, couple of, so the phase plus K modulation is more accurate. And a couple suggestive observations. Okay, this tells us that we expect that V should be this, what's it right here? K star. Yes, this should be the K modulation plus faster decaying term. So we hope that this is the behavior and the rest is error. This rest is Z. And if we want to compare U tilde and the full phase modulated guy, this is like, we just computed it. T to the minus 3/4. So we've got two things to work with. And now this is a tricky point. Okay, so now we look back at the Witham equation. It's a scalar conservation law, characteristic speed omega prime. Okay. Now, here is our theorem. So now taking this same kind of non-localized data, so this is just the same assumptions as the previous result, and define K Witham, KW, to be a solution of 2 with data H sub x for K. Because H is like psi, the phase shift, and K is psi sub x in this formalism. So we should take H sub x for K. All right, and we're going to take, for positive time and high norms, if we take K, here it is, then we will and define psi w by the antiderivative of KW, then here are our estimates. If we subtract from U tilde the fully modulated K and psi variable, this is from the Witham equation, we get t to the minus 3/4 plus eta decay, where eta is arbitrarily small and positive. That's our way of accepting the log term in a way that goes through an iteration, the usual thing. And then the bounds on K are, K is bounded by a heat kernel, and the difference between psi Witham and psi, which is our old psi. So we didn't define psi by Witham equation. We defined it kind of operationally, what would make things small in a certain way. But the difference is also small like a heat kernel. Oh, that's, okay, that is Sonnstetter, Schneider, Schiel, Schneider, sorry, and student of Schneider. I'm blanking on the fourth name. Sorry, but it's a paper around the same time. Yeah, and that ooh. Yeah. There we go. That's okay. So this is very satisfactory, especially because now when we solve the Witham equation, this has been done to death. This is a scalar Burgers, basically, And we know that we can get lower bound as well as upper bounds for this. So it does decay like a heat kernel, that's known. So it's not just less than, it's at this rate generically. So long as the integral, if the integral of k, if the integral of h is 0, it in fact decays faster. That's known, right? Zero mass decays faster. But so long as the integral is non-zero, this decays like a heat kernel. That is the behavior. So now we have a lower bound and an upper bound. And the lower bound is heat kernel rate, and the upper bound is faster. So we have the behavior, and the behavior is exactly the Witham behavior. A funny point, though, is that this estimate is not as sharp as the difference between what we constructed and U tilde. That decays a little bit faster. So we actually have something that's better than the Witham, but it's less precise. We don't know what it is. But yeah, so this is my experience with the Witham equation and formal equations in general. They always seem to work, but sometimes it's surprising how they do. And sometimes you can see more by another technique. Usually it's hard. Usually you need another technique to prove it. At least I have. Okay, so.
Scale of your method can tell you what you should.
Well, our method can, or what the correction should be? Oh, that's a good question. I guess you could. I mean, I think you could. Yeah, I think you could. My feeling is you could. I haven't done it or even tried, but watch the next few slides and maybe you'll see how it would happen, I think. Okay, so, all right, and for systems that have additional conserved quantities, so if you did, instead of reaction diffusion, if you started from a conservation law, or a relaxations, or a hyperbolic-parabolic conservation law, possibly with some so convection, reaction, diffusion, then the Witham equation becomes a system with multiple speeds. And so, and it's not accessible by the renormalization, at least not that I know of. I don't know how to do it by renormalization. So these methods that we're using seem, they're really designed for this case. Okay, so now how do we prove that these are comparable? Okay, so it's sufficient to show that our K minus K Witham is small in LP of the order stated. Okay. First observation. So there's some general theory of constant scalar conservation laws, parabolic type, that says there are some asymptotically irrelevant terms. So any power in the nonlinearity higher than 2, you can throw it out. And what else? And the diffusion can be fixed at a constant at the background state. So you can replace the Burger's equation by this sort of linearized version. This is just constant coefficient. And then the only part that's left over is, terrible. This should have a derivative. This should be a derivative of k squared, or it's not going to work. That's a typo, sorry. Right. Yeah. Okay, so just a forced constant, a convected heat equation with a quadratic forcing, a differentiated quadratic forcing. And that, I mean, that is Burger's now. And you could solve it by Hopf-Kohl transformation or do whatever you like. So that's interesting.
Second derivative, K squared double root.
Just a first derivative. It came from the expansion of omega. Yeah, it's the second, E star is the second derivative of omega. Okay, yeah. Yeah. And then the second derivative came only from the diffusion term, which was d of k, dxk with another dx, but the diffusion coefficient can be frozen. It doesn't affect the asymptotics. So this is what you get. And now it's something that's very solvable, completely solvable. And in fact, we know the solution operator for this part. It's just for a convected heat equation. It's just the convolution with the heat kernel. And an important fact is that these coefficients, A star, D star, relate to the spectral expansion of the critical mode. And they are, as one would expect from all this, or I mean, it's the only way it could work, that it's the convection and the diffusion. And then there's this nonlinear term, but that's not in spectral theory. So that's very nice. Okay, so the solution operator of the constant coefficient part, so the left-hand side up here, it's the x derivative of this solution operator will approximate dx of SP applied to H naught G. Those are the key estimates that I spent so much time on, called the linear modulation bound. And I see that by knowing this. That's how I know that. Okay, so now I kind of like this argument. I'm calling it a reverse Duhamel argument. So it's like reverse engineering what you know. So we have that. Okay. So knowing that we can well approximate source terms by the sum of periodic solutions times Gj. Oh, what is Gj? Suddenly, the Gj. Yeah. Yeah, here's my data, applying it to periodic solution. Okay. So we can find that for our psi, the one that we developed by implicitly through our Duhamel iteration scheme, this satisfies little psi of t. That's the solution operator for the linearized Witham equation times the data plus the Duhamel version of the same E star psi x squared. This would be exactly the Duhamel. This would be the Duhamel representation of the solution of the linear of this equation right here. It's exactly that, but I'm not using k Witham. I'm using the derivative of which would be the derivative of psi Witham. I'm using the derivative of psi. Okay, and I'm saying that this is still true up to an error term, because there were a bunch of residuals that I threw out in transforming the original formula to this. And they have a decay rate of t to the minus 1, it turns out, in L1. Okay, but likewise, for the Witham equation, we can write, by the same sort of trick, we write the Duhamel formula for the simplified equation, this Burger's equation. But remember, there were some what I called asymptotically irrelevant terms. There were some error terms, higher order terms in all the Taylor expansions of everything. And the fact that they're asymptotically irrelevant is captured by that there is another residual that has the same decay rate. So if I subtract them, I get the same Duhamel with R tilde of the same, or remainder of the same rate, same error bound. And now I'm defining delta to be the difference between the two. So I pull out a delta in the quadratic term, but then there's also, I'm just using the difference between two quadratics here. There's the sum and the difference. So I get delta plus the sum. And now I have an expression for delta. And I have, okay, so now I need to do an iteration finally. So I define nu of t to be the soup. It's another bootstrap argument with, I'm trying to shoot for a different decay rate. And I will get a bootstrap argument. And that is going to give me this decay rate for the difference between K, this is K with them, and this is R, dx of R psi. And that's what we needed to show is small in order to, going back to observations A and B, that's exactly what you need to show rigorously the decay rate of the WISM. And there was an R tilde, but it's smaller, it's t to the minus 1. And this goes between t to the minus 1 at L, let's see, infinity, but down to t to the minus 3/4 at L2 when p equals 2. And so it gives us, in the end, what we expect. It gives us more. It tells us more sharply for which LP you get what. But in the end, we just found it nice to put 1 decay rate. That's the end of the proof. So it's kind of I like it because it's kind of a nice way out of what could have been pretty complicated, a lot of complicated estimates. But it's just this comparison of two Duhamel formulas. And now, okay, so now just make a few comments motivating the next lecture. Okay, so of course, we have plenty of examples of periodic patterns and traveling waves. I really enjoyed the recent talk by Avi Wigderson on reading Turing, and he made there was one sentence in there, I don't know if you remember, but I always say this. He said, if you Google the hits in math papers, probably Turing bifurcation or Turing, pattern, that's going to be the biggest number of hits. It just really captures people's imagination. It captures my imagination. It's a great, one of the great ideas in history. Okay, and so this work, but there's plenty of work after by Vitor Eckhaus, by Alexander Mielke, Schneider, Sandstetter, etc., extending this. And now we have not only the existence of such patterns, but their stability, which I guess Turing also discussed a bit, but not only that, behavior of nearby solutions. We have all kinds of descriptions. So that's what we're trying to get here. These were mostly for small amplitude, but then we have WISM. The WISM expansion, that's valid for arbitrary amplitudes. Assuming, but we made an important assumption there, spectral stability of the background periodic wave. So that's what you get from small amplitudes, I guess. Guarantee. You don't have to make that assumption. Okay, now, systems that have conserved quantities, they don't fit that theory. So instead, here's what you get. So let's look at a generalized periodic traveling wave, a periodic traveling wave solution. This is a vector valued solution, but now it's not a pure reaction diffusion. We allow some convection, some diffusion as before, but also partial reaction. Some of the terms do not have any reaction. And so we'll take we'll assume R of the coordinates of U have no damping on them or growth. That means the first R coordinates satisfy a conservation law, and it means that those first R coordinates are densities whose total integral does not decay, or rather is conserved. Okay, and we're going to look at stationary solutions equivalently of the co-moving frame equation. And the extremes are, of course, if R equals 0, there are no conservation laws. That's the case we just treated, it's reaction diffusion. R equals N is conservation laws, there are no reactions. But there can be all sorts of things in between. For example, here are the Saint-Venant equations for shallow water flow on an incline. And written in Lagrangian coordinates, it looks easier. And you see, just looking here, R equals 1. The first coordinate, tau, which is the specific volume, 1 over the height, rather, it satisfies a perfect conservative form equation. And so its integral is conserved. And the second equation doesn't. So it has some damping. Here's an important one for us, the generalized Kuramoto-Sivashinsky equation. It has a Burger's equation part, it has a KdV part, epsilon u xxx, and then it has a Kuramoto-Sivashinsky part, which is this delta uxs plus delta u fourth derivative. So if you take epsilon equals 0 here and delta equals 1, you have Kuramoto-Sivashinsky. If you take delta equals 0 and epsilon equals 1, you have KdV. And all sorts of things in between can happen. These are all relevant to thin film flows on different inclines. So I would say you could think of the KdV limit, that's flat. Kuramoto-Sivashinsky is vertical, and in between you have different angles. But then here's another one, viscoelasticity with a surface energy. That's a pure conservation law. Or Complex-Ginsburg-Landau equation, okay, famous R equals 0 case, pure reaction diffusion. Very interesting behavior. And okay, so here's Turing again. Oh, I misspelled his title. Very famous. And I'm going to contrast that. So Turing bifurcation is a bifurcation from a finite frequency, a wave number that's bounded from 0 and bounded from infinity. So it has a steady, we can predict the frequency. This is what's called a long wave instability, this here. This is a very beautiful phenomenon called roll waves. It occurs in very slightly inclined canals, and you see, maybe you can't see, but it's a long run of periodic, they almost look like solitary waves. They're so spaced apart, but it's a periodic wave train. Okay, and I'll just mention, so many people, right, I mentioned a few of them, Korteweg, De Vries, there's many, long wave expansion, so many people, but I particularly like this modified Kawahara equation. That's kind of the one I showed you, the generalized KdV Korteweg, and it covers very many cases. And it was very important for our analysis, which was centered around Saint-Venant equations. Okay, reproduced here. Okay, here I've written it in Euler form. H is the height of the fluid. It's a little more clear what's going on. U is the velocity of the fluid. F is a non-dimensional Froude number. It's kind of measuring this inclination. And it looks like, yeah, it exactly looks like a gamma log gas with gamma equals 2, which would be non-physical. And then some source term, H minus U squared. So what's that? H is gravitational force, which is proportional to the height. Minus U squared, that's a turbulent bottom, a turbulent friction from the bottom, which often taken to be quadratic. I think that's called the Chesi approximation. Okay, you can introduce, so this predates us, introduce delta to be square root of F minus 2, tau to be 1 over H, rescale time, and rescale tau, u, and x. And what you get is formally the KdV Kuramoto-Sivashinsky in tau plus an error term like this. Okay, some error term. All right, and this is known, I mean, that's one instance of the kind of thing that Nepomniachtchi and Barr and others were doing in general, or general equations. And notice, let's see, some things to notice. So, I should tell you a few things. When F is bigger than 2, you don't get any periodic waves. The constant solution is stable. The bifurcation here, the Turing bifurcation, broadly defined, occurs at F equals 2. That's where the laminar flow with everything flat goes unstable. And that's where you expect some pattern formation. But it goes unstable at 0 Fourier frequency. And that is going to tell us that the period here is delta over nu. Where did nu come from? Oh, nu is the, okay, no, that's not the period. Where's the period? Period, 1 over delta. There we go. It's infinite period, long wave. So here's an existence theorem. We can expand the periodic traveling waves as, okay, these are the solutions, these are on the right-hand side are the solutions of the generalized Kuramoto, the KdV-Ks, whose existence was proved by Nick Ercolani before, because that equation has its own life and its own more importance, completely general. So it had been well studied. It's not easy at all to prove this. Okay. Yeah. So we did. This is in the oh, I put 13, but it came out in 14. I guess that was the archive. It's in this is our paper for systems. It's in Invenciones. This was no. It's called Stability of Generalized Kuramoto-Sivashinsky waves, I think, or no. This one is onset to from onset to infinite Froude number. It's something like that. It's about the Saint-Venant, viscous Saint-Venant. Yeah. So this is one of the things we showed is that so the profiles converge and appropriately rescaled converge to these KdV profiles. These KdV-Ks, which, by the way, were already shown to approach to KdV waves as delta goes to 0 by Ercolani. So taking both together, we get convergence to conoidal waves, periodic conoidal wave solutions of KdV. After all this rescaling, in well, it would. What did we prove it in? Well, remember, it is on period 1 after all the rescaling. So almost Sobolev for anything is almost the same, right, on bounded interval in L infinity and in higher Sobolev nodes as well. I guess as far as we want to go. Yeah, but this is mostly just following what others have done. Okay. All right. Okay, so if you have a standard Turing instability, the existence and the stability, they both relate back to a constant background state, right? You look at the Fourier symbol of the background state, and then you do some kind of Lyapunov-Schmidt reduction, projecting out the kernel, getting a reduced equation. The operators you work with are all for that constant coefficient background state. Here, there's not really, the background state is a singular limit. It's a rescaled state. It's these conoidal waves, but somehow spread out to infinity and shrunk down to nothing. So you have to do a rescaling, and you have to do a stability analysis for KdV, which is really, really hard. I could say that, but that's not what we did. I'm talking about the spectral stability. That was done by others. That was, okay, maybe better that I don't remember the groups, because it's a funny story to me. So at that time, there was big separation between the former Soviet Union and the US, not much communication. In the former Soviet Union, there was a proof that the conoidal waves were unstable. Followed within about 5 years that no, they're stable, and here's the error. It's a really hard analysis, but subtle error. Over on the US side, it's a repeat. Someone shows it's unstable, and then someone else showed it's stable. I think that proves it's a really hard problem on either side. Okay, but so others have described the stability, and there's a paper by Barr and Nepomniachtchi. They use amazing numerics, and they carry out the singular perturbation at a numerical level and verify some rigorous analysis, some numerical, and show that show strong evidence that the KdV KS singular limit is stable as well, spectrally. And remember, we were always going to assume in all these analyses, we assume spectral stability and then we prove something. But you have to prove spectral stability. And it's gets much more intricate in this case. So even if you just look at the ODE level, Turing is it's like a Hopf bifurcation. This long wave is like a Bogdanov tuck. It's a saddle node collision. And it has a whole unfolding that has about 10 different pictures in the unfolding, like lots of different cases. The main one being a saddle node. That's where you get the periodics. Okay, so okay, so this is for fun, if you find it fun, just to show. So this was a question I just asked myself. Could you have standard Turing instabilities for conservation laws? And you can just write down, it's really a question about the Fourier symbol, and that's just linear algebra. So you linearize, you get a constant coefficient equation, ut plus aux equals duxx, that translates to this symbol. And the question is, could you have dissipativity for large C and plus, so could you have dissipativity at large frequencies and small frequencies? Here, C should really be K. C is my Fourier number. And yet, you have the maximum real part occurs exactly at 0. So you have neutral instability. Could this happen? And that's interesting because it means A would be then strictly hyperbolic. So that replaces, without a C, this is the reaction diffusion case, and you wanted A to be stable. Here, it's just going to be neutral. That's the best you can have. And D would have positive diagonal entries by some matrix perturbation expansion. Okay, and the answers are, but you have to prove it. No if n is 2 or smaller. No if they're simultaneously symmetrizable, but yes, in general. So you can find them. And yeah, so I'm still looking for a really relevant one with all conservation laws. I haven't found that yet, but I was looking for these before we ever found them. I was also looking at stability of periodic waves for a long time, just because I admired Rob Gardner's work on periodic functions. I wanted to do it for conservation laws. I thought it would be maybe kind of easy, and it was so hard. And also I had no physical example. So that's a hard combination to overcome. You feel like, well, I should probably just put this in the drawer, but it was so interesting. I kept with it, and luckily Miguel Rodriguez and Pascal Nobla came along with a great example of these roll waves, and it's so exciting to find they were stable, and they work. Okay, so we'll continue with the theory of the systems, the rhythm system now in the next lecture, and I think the behavior is really fun for the systems. Okay, so wow, I'm on time today. Any questions from outside?
So in general, for system back in the first part, like, can you check those spectral?
In general, not rigorously. We do it numerically. But I do want to mention, so the small amplitude ones, that has been done rigorously. Yeah, I think it's in the very next slide on the next lecture by my former student, Blake Barker, using a numerically assisted proof. He did this, that was his amazing thesis project. And this involved, so just to give you an idea what's going on. So in the Bar and Napamiaski paper, which used numerical, it had a numerical part. It wasn't with guaranteed error bounds. but it was done very nicely with a numerical convergence study and things like this. But they were losing 50 decimal places. So they would have a truncation error of 10 to the minus 50 to get what they needed to show was between, strictly between 0 and 1, and they would get, that's what they needed, 50 more places. So they had to use extremely high precision, arbitrary precision kind of arithmetic, which at that time they had to program themselves. It wasn't that available. So this was a real tour de force. A lot of elliptic integrals in there that have to be estimated and things like that. What Parker did was he used the fantastic interpolation properties of analytic functions to everything in sight was analytic, and so you can you can kind of upgrade. You can do a refinement. You get a very crude error bound, and you can improve it by a lot by interpolation. So if you have a bunch of crude error bounds, you can put them together and get gain. You get exponential gain in the number of exponential convergence in the number of data points, which is exactly what you need to deal with a loss of 50 decimal places and do rigorous analysis. It's a fantastic result. And so we do have one rigorous result, which by referring to his work, but it's computer assisted. It's very complicated.
So here's where you have spectral stability. I mean, you use spectral stability for linear stability.
Yes.
So let's say in the case where you have your essential spectrum with one mode at 0. So how do you check that you don't have like eigenvalues that are
Oh, but so we would for our nonlinear stability analysis, we assume that away. That was not allowed in our assumptions. However, maybe when I talk about the KdV limit, we know that has all essential spectrum in the stable case. This is what you're trying to show, is that plus some information on dispersion, right? Some monotonicity in frequencies in the dispersion relation. But so that's what they're showing. The Bar and Nepomniachtchi and Parker, they showed that as you increase delta was the singular perturbation parameter. As you increase delta, things move away from the imaginary axis and in the good direction. That's the whole business, which is a different problem. That's not I should also say, a caveat is that our nonlinear stability estimates, they blow up as this amplitude goes to 0 because everything in sight is getting a huge coefficient. So so there would be an interesting problem to do if you allow arbitrarily small amplitude, get close as you like to the KdV limit. You would have a problem there due to the absence of a nonlinear stability result for the clinoidal waves themselves. We have nonlinear stability of these perturbations, which estimates degrade as we go toward the clinoidal wave. Usually it's right for the classical touring, it would be very different. You get rigorous bounds all the way down to the bifurcation point, and they improve if anything. But this is not, we don't get a strong result, you could say. By the way, though, fruit number 2 is where things break down. What do we see in nature? Fruit number 8 to 15 or so. So in actual data, so there's some famous work by Brock, who did when he was a grad student at Caltech. He must have had a tough advisor. He did so much, and he did actual measurements on the now I forget the name of there's a Los Angeles water delivery system. He did measurements there. He did measurements in the So in the wild, I think he tabulated data from other people, and then he compared it to data in the lab. What was the lab? It looks from the pictures in the paper like it's the Caltech hallway, and he's put up some some rain, the gutters from your house that catch rain. He put some prepared things about 60 feet long, very gradually inclined, and he measured it with amazing with wires that moved up and down and made a little mechanical graph of the waveforms, and they're all perfect. I mean, they match the equations beautifully. He also had to do a boundary layer analysis to make them match, because actually Saint Venant doesn't match near the boundary at the peak of the wave. He did all this, and that was around 65, I think. So yeah, that's all I have for now. Okay, two more things. So the next one is I think yeah, there's some less technical, more graphics. I think you'll like the graphics. Yeah, some nice pictures of behavior. Yeah, thanks for your loyal attendance. Appreciate it. Any questions out there? Thanks for your loyal attendance. All right. See you on Thursday then. Hi, yeah. Lots of friends out there. Okay. Enjoy the rest of your week, all of you, and see you in a couple days.
See you.